All right, good morning, everyone. Happy Friday. We have made it to the end of the week. So hopefully our topics that we have today are interesting enough to get us through to the weekend. So we left off yesterday talking about recipes, and so how we could use specifically the recipes package to do our pre-processing of data for us to help prevent data leakage. And our example we were using was the Ames housing data, again, trying to predict the sale price from all of the other variables that are in the data. And what we wanted to do was to use a principal components analysis. So rather than using all of the variables as predictors, we wanted to pull out the high-level components and use those as the predictors in our model. And at the very end of the day yesterday, we were talking about this function here, which is step PCA, which is a step that we can add to a recipe, which will create principal components for us. And here we're specifying 5 principal components. Okay, so if you have not already, or if you closed it out from yesterday, go ahead and open your recipes exercises. That should be number 13 in your exercise folder. Run that setup chunk. And then we want to build a recipe. So again, we'll start with that recipe function that has the formula and the data that it'll use for a template. And then these are all of the steps that we want to add to our recipe. So at the end, you should have the recipe function plus 6 step functions that will make up your full recipe. So we will go ahead and take a few minutes to work on this and then come back together. All right, so let's build this recipe. So we're going to save it as PCA recipe. So I will start with that. To initialize the recipe, we use the recipe function and we give it a formula so that it knows which variables are the outcomes and which are the predictors. So here again, I'm saying sale price is our outcome, and we're going to predict sale price from all other variables in our data. And we'll use the AIMS data again as our template, so it can identify the variable types. All right, so then we add our steps. The first thing we want to do is add a novel level to all of our factor variables. So that is step novel, which we saw yesterday. And we'll apply that to all of our nominal variables. The next thing we want to do is convert all of our factors to dummy variables. So we can do that with step dummy. And again, we'll apply that to all of our nominal variables. The third step is to catch any zero variance variables. So that yesterday was step ZV for step zero variance, and we're going to apply that to all of our predictors. Step 4 is to center all of the predictors. Just step center, and again, apply to all predictors. Then we scale all of the predictors, which will be step scale. And the final thing we want to do is compute 5 principal components. And so again, that will be step PCA, applied to all of our predictors. And here we also specify the number of components we want to be 5. Okay. And so that is our recipe. And so if we look at the output, like after we run this, what do we get back? So if you look at the PCA rec object, you see that it's a data recipe. It tells you we have 1 outcome and 80 predictors in our model. And then it tells you the operations that this is going to do. And so again, this is not a trained recipe. So it's just telling you the steps, right? So it's just saying we're going to do a novel factor level assignment for all of our nominal variables, right? It's not giving you details of exactly what is happening to individual variables because this recipe hasn't been trained yet. All right. So we're going to talk now just a second about these roles. So again, the roles we have right now are outcome and predictor, but we can assign different roles. And then select by roles. So there is a has role. So if we wanted to assign a role, so for example, we could update the role for certain variables, for example, to the new role of privacy, then we could apply a step function to only those variables that we had given the role of privacy. So you're able to add or remove roles as you need to in order to help select variables. You won't have to do that too often, but I just wanted to make you aware that that is a functionality that exists. Another good example is if you have an ID variable in your data that you don't want to get rid of, but you don't want to use the ID as a predictor, for example, since it's just a random number usually, you can update the role for that ID variable to be like unique ID or something, and then it won't be used as a predictor anymore. Okay, so now if we think to our workflows that we talked about yesterday, we could use add model to add a model to a workflow. How do you think we would add a recipe to a workflow? So we're going to try and figure this out. So it is probably exactly what you think it is, but go ahead and try to make a workflow that combines the PCA recipe that we just made with the linear model specification which was in the setup chunk of your exercises. So take a couple minutes and try and create this workflow. All right, so let's make this workflow. So I'm just going to call this our PCA workflow. PCA. All right, and so we create a workflow by first initializing it with the workflow function. Then we can add our model like we normally would with the LM specification. And then to add a recipe, it's just add recipe. And we tell it we want to add the PCA recipe that we created. And so we can run that. And now if we look at our output of that workflow, we now see that it has the preprocessor as a recipe. Yesterday when we were doing workflows, it said the preprocessor was a formula, but now it's a recipe. And it tells us that our preprocessor has 6 recipe steps. So it tells us everything that it's going to do. And then we still have our model specification at the bottom. So again, all of our pre-processing modeling is all kept together in one place with this workflow. And so again, it's the add recipe function that will add a recipe to your workflow. So question, do you need a formula in your workflow if you have a recipe? The answer is no, because again, the formula is actually in our recipe when we initialize it. So when we create that recipe, we are specifying which variables are our outcomes and which variables are our predictors. So we don't need to add formula to the workflow. We just add the recipe. All right, so let's try our new workflow. Let's fit the PCA workflow we just created to the aims folds split object, which should be run in your setup chunk. So when we fit these, what is the estimated RMSE? So we're going to fit these models and then calculate the metrics for it. All right. So to fit these models, again, since we're applying it to our folds, we'll use the fit resamples function. So we'll take our PCA workflow that we created, use fit resamples to fit that workflow to our folds, and then we can use the collect metrics function to get our metrics out. And again, by default for a linear model, that'll be the RMSE and the R squared. We could, in the fit resamples function, specify different metrics, but the default are fine for us for now. And so we see that the RMSE of our workflow is just under 39,000 and an R squared of 0.76. Was everyone able to get results that were at least similar to these? Yeah. Yep, they won't be exact. There's going to be some randomness, but yeah, should be close. Great. All right, and so just like we could update models or update formulas in our workflows, we can also update the recipe. So we could take our same workflow and just quickly modify the recipe if we wanted to. And so we will try doing that. So we're going to create a new recipe that's going to be similar to the recipe we already created, but instead of centering and scaling the data, we'll use a box-Cox transformation. So you'll need a new step to your recipe that we haven't talked about yet. If you type step underscore and then tab, you should see a list of all the different step functions. You can look through there and try and guess which one you need. Or again, all of the steps are listed on this on the recipes website. So you can look through there, but build this new recipe and then update your PCA workflow to use the new recipe. Okay. So we'll take a few minutes to create that new recipe. All right. So to create our boxcox recipe, this is the same recipe code we had earlier, except now instead of step center and step scale, I've replaced both of those lines with step boxcox. So that's the new function. And we're applying that to all of our predictors. And then we can create our boxcox workflow by taking our existing workflow and then just updating the recipe. And so if we were to fit this new workflow, we could fit it exactly the same way, just piping our workflow into fit resamples, and we'd get an RMSE of 44,000 and an R squared of just under 0.7. So this boxcox transformation is leading to worse predictions than centering and scaling was. So that's kind of a high level overview of feature engineering. So like before you like pull these features out of your data, it's just like this young, innocent little data set. But then we can extract all of this extra knowledge and wisdom from it by pulling out additional features from our data that may not be exactly clear just looking at the raw data. So let's switch now to some Stack Overflow data. We saw this before, looking at predicting the remote status of employees based on different characteristics about them and their job history. And so we're going to start with a little bit of a refresher on what we've been doing so far. So go ahead and pop in the chat or feel free to unmute yourself, just which packages are doing these different things, right? So this first piece is splitting our data, right? Or creating new samples from it. So which package within Tidy Models are we using to split data? So for splitting data, we're going to use the R sample package, right? So we're creating different samples of our data. And what about for creating our model specifications? Which package do we use to define our models? So our models are going to be defined using the parsnip package, right? So this is our cute little parsnip guy. And then for our recipes, we are using the recipes package. So again, we're very into food and Tidy Models. And then finally, to create our workflows, we use the workflows package. And we have our fit function, which is going to fit just one data set. So if we're not using resamples, we can fit our workflow to like all of the training data instead of folds, and we can get predictions out of there. And again, we have the ability to predict class membership. So what is our expected class, either remote or non-remote, or we can predict probabilities. So what's the probability that an individual is remote based on their other characteristics in their data. And finally, we can fit metrics, or not fit metrics, but estimate metrics based on our fitted model and the predictions. So question in the chat, are these part of Tidyverse or separate? So these are separate but related. So they're part of the same ecosystem, but different package suites. So there is the tidyverse, which is what we talked about at the beginning of the week, and that is like dplyr, ggplot2, tidyr. So hopefully some of these are looking familiar as things that we talked about early in the week. And then these modeling packages are part of the tidy models suite of package. So tidy models is like the tidyverse. It's a set of packages, but where tidyverse is more focused on data manipulation. So creating new variables, filtering. Tidy models is going to be focused on just the modeling part of it. Yep. All right. And again, with our metrics, we have the ability to like create our own set of metrics with the metric set. So here we say we want accuracy and the area under the ROC curve, but we could change that. We could use metric set to say we want accuracy, area under the curve, sensitivity, and specificity, and then we'll get all of those outputs as well. So when you look at something like this and you see that we have accuracy of 90%, that seems pretty good. But our ROC AUC, so our area under the curve, is only 0.5. So that's not good. If you remember when we first talked about area under the curve, we said that 0.5 was basically just randomly guessing, right? And we see that our specificity is 1. That's very good. But 0 is very not good for our sensitivity. So does anyone have a thought as to what this, what the confusion matrix might look like if we made that 2x2 matrix? So what's happening in our model is our model is actually predicting that everyone is not remote, right? So that's not what we like to see, but that's what our model is thinking is happening. And that's what's giving our ROC AUC is just like a straight diagonal line, which again is not great predictions. And so what's happening is that in our training data, the vast majority of people are not remote. And we see the same thing in our testing data. And so what's happening is that because the remote class is so infrequent, our model says, you know what, if we always pick the not remote class, we're going to do a pretty good job of making predictions. And that's not necessarily wrong. I mean, when we looked at our metrics a few slides ago, we saw that 90% of our predictions were correct. But we can do a better job of that. Oh, there's another question in the chat really quick. What kind of research designs or data analysis one might apply these to beyond regression? Yeah, so there are many places where like this type of machine learning can be useful. Often it's in places where we care more about prediction than explanation. So a lot of times you'll see this in industry. So if you think about companies like Amazon, for example, they want to predict what you will buy based on what you have previously bought. They don't really care why you might buy these new things. It's all about like, can we make good predictions? Same thing for like recommender systems. So like Netflix wants to recommend new shows to you based on what you've watched. So these models in general are much more focused on predicting behavior than explaining behavior. So if you are focused on like creating a causal model to explain why someone behaves in a certain way, like a random forest is probably not going to be a good model for you to use because you're not going to get coefficients or anything out of that model. You can get variable importance plots, which we saw yesterday and which we'll see again this afternoon for our case study, but it's not quite the same thing. Does that help answer your question about when these models might be useful? Awesome, great. All right, and so here the issue that we have is our classes are really imbalanced. And so we want to see if we can get better at identifying that less frequent class. And so the way that we can do this is through subclass sampling, right? And there are a few ways that this can happen. One is through downsampling. And so for downsampling, we are basically reducing the number of people in the larger class. So here you can see that some of the blue dots on the left are missing from the right. So we've reduced the size of that larger class. And then the opposite of that would be upsampling. So we can kind of resample our smaller class to more equal out these class sizes to get better predictions for our smallest class. And so we can do this with recipes. We can do upsampling and downsampling. I'll let you explore those functions again, find out which step it is you need to add. But we want to add a step to our recipe. And I believe that a Stack Overflow recipe should be in your workbook already. Yes, so there's the Stack Overflow recipe. So we'll just add a step to this existing recipe that you have in your notebook. Then we want to downsample the remote variable majority class in our training set. So we will edit that recipe and then update the workflow and then refit the model and examine the new metrics and see if our area under the ROC curve did in fact improve. Okay, so to make our new recipe, I've called it Stack Overflow down, since we're going to be downsampling. Took our original recipe and added a new recipe step downsample. And we're wanting to apply this to our outcome variables, right? We want to apply it to that remote status. We want to downsample that large majority class of our outcome variable. So here we're applying it to our outcomes and not our predictors. So then we can create a new workflow, which again, I've just called our down workflow. And I created that by taking our original workflow and just updating our recipe to use the new Stack Overflow down recipe. And then we can fit the model. So again, we just send that workflow to the fit function and fit it to our training data. And finally, we get our predictions. And I got the predictions as both our class predictions and our probability predictions. And so if we look at our metrics, we now see that our accuracy has gotten worse, but our other metrics look much better, right? So we're not just always predicting the not remote class, right? So we're using more of our information that we have in our data. And now our ROC curve looks a little bit better. It's not a great ROC curve, like we're not making super accurate predictions here, but we're doing better than just chance guessing. Okay. All right, so just a couple last things about the recipes package. We can get the pre-processed training data back from a prepped recipe if we want to by using the juice function. Again, we don't have to do this because the workflow and everything, the fit functions take care of all of this for us. But if we're interested in what the downsampling is doing, this can be helpful. So if we look at our original training data, again, we had this large class imbalance. But if we apply our recipe, and so we train our recipe on the training data, and then we juice that to get our like our prepped training data back out, then we see that we now have balanced classes, right? So it downsampled this not remote class. And so now we have balanced classes that are used for actually training the model. And so by default, the downsampling is performed on the training set only. So that just helps us fit our model for our like fitting it. Once we have the coefficients for the model, in this case, since we're using a linear model, we don't need to downsample the testing set because we already have those coefficients set. And so if we were to train our recipe and then apply our recipe to the testing data, you can see that our testing data is not downsampled. We still have the class imbalance there, but that's fine because we're just making predictions. We're not actually trying to figure out what those coefficients are. If we were doing a decision tree, we're not trying to find the splitting rules. We're just applying what's already been estimated. All right. So that is our high-level overview of feature engineering using the recipes package. Does anyone have any last-minute questions about this before we move on to the next set of slides? No? All right, well, I will go ahead and switch over. All right. So we are now going to talk about model tuning. And so this is something that We've kind of briefly talked around a couple times yesterday, but now we're going to actually look at how we can figure out which parameters we should be using for these models, and specifically parameters that we cannot estimate from the data directly. So go ahead and open up your tuning exercises and run the setup chunk. I'll do the same thing just so we're all in the same place. We're almost at the end, our second to last exercise. All right. So for model tuning, we'll be using the tune package. And again, there is a chapter in the Tidy Models with R book about model tuning and the dangers of overfitting, and how the tune package can help us avoid that. And so we're going to play with the tune package this morning and look at how we can make sure our models are estimating as best as we can. All right, so we're going to start with the K and N models. And again, this is the K nearest neighbors. And we've seen previously that we can make a nearest neighbor model in Parsnip using the nearest neighbor function. And we specify how many neighbors we want to use for each of these data points when we fit this model. And so far we've just used neighbors of 1, right? But it's neighbors plural. And this can be used for regression and classification models. So the question is, like, which number of neighbors should we actually be using, right? This isn't something that our data can specifically tell us, right? It's not a beta coefficient in your regression model that gets estimated. We have to specify this before the model gets estimated. So we're going to explore how we can do this. The first thing that we want to do is run our new recipe. And so this is already in your R Markdown document. So you can go ahead and just run this code. And there is a model specification that is going to fit a K nearest neighbors model with 5 neighbors. And we're using the KKNN package as our engine. So what I would like you all to do is create a new workflow that uses that recipe and the model, and then fit the workflow to the CV folds data object. And that was created in our setup chunk for us. Right? So we're going to fit this workflow after you create it, and then calculate the RMSE of this model. All right, so the first thing that we do is create the workflow. As we initialize our workflow, we add our recipe, which again was the normalized recipe, and we add our model, which was our KNN with 5 neighbors specification. And then we fit this workflow just like we've been fitting all of our other ones. We can pipe it straight to fit resamples, and we use our CV folds, and we collect our metrics, and we get our average RMSE of 37,000 and an R squared of 0.786. Did everyone get similar numbers to this? Yeah. All right, well, we're going to keep fitting a few more of these models. So now we're going to repeat that same process with a similar workflow, but this time we want to use 10 neighbors instead of 5, right? So you'll need to update your model and then create a new workflow and fit that model and see how our RMSE or our R square changes. All right, so this is going to look very similar to our last example. The first thing that we'll do is create a new model specification. So here I've called it KNN 10 spec since we're using 10 neighbors. So we specify a nearest neighbor model with neighbors equals to 10 this time, using our same engine and still using regression. And then we create our new workflow. And here I'll just take our existing workflow and update the model. So it'll still be using that normalizing recipe, right? Because that was part of this workflow that we're now just updating the model for. And then we can fit this workflow. So we'll pipe that directly into fit resamples, tell it the resamples we're using, and collect our metrics. And so with 10 neighbors, we can see that our RMSCA got better. It's now just under 36,000, and our R squared is now above 0.8, right? So 10 neighbors as opposed to 5 neighbors improved our predictions. But what is the best value? Like, is 10 the best we could do? Or would 15 be better? Or maybe actually 8 neighbors would do better than 10. And so what we want to do is find a way to fit several models with several different values and then compare them all easily without having to specify each separate model. And so our tool for doing this in the Tidy Models framework is going to be Tune Grid, right? And we are right up on a break, so we will go ahead and stop here for 15 minutes. And when we get back, we're going to talk about Tune Grid and how we can tune that neighbor's parameter from our model, right? So it's 10:10 at my time. So we'll come back at 10:25 Central Time to talk about tuning. All right, go ahead and give me a thumbs up or let me know in the chat if you're back. Awesome. All right, so let's continue talking about model tuning. And we're going to do this using the tune grid function. So the tune package contains a few different functions for fitting and tuning models. And again, you can find a bunch of information on the tune website that I've listed here. And the function that we're first going to use is the tune function. And this is really a placeholder for hyperparameters like the neighbors that we need to tune, right? So instead of specifying a specific number of neighbors, we drop this tune function in to say, we don't know how many neighbors we want right now. We're going to figure that out. And so that goes into your model specification. And then we can use tune grid. And so tune grid is a version of fit resamples. So we'll use it very similarly. And tune grid is going to perform a grid search for the best combination of tuned hyperparameters. So for this specific example, we only have one hyperparameter, it's the number of neighbors, but we could have multiple hyperparameters that we're tuning. So for example, in our random forest model yesterday, we had the tree depth and the min in, which was the smallest size to split. So we could tune both of those at the same time. Okay, and so tune grid will take an object, and this can be a workflow, a formula, or a recipe. For us, it will mainly be a workflow since we're keeping everything nice and tidy together. If you're not using a workflow, you can also specify a formula and a model or a recipe and a model, but I would recommend using the workflow for reasons that we talked about yesterday. And you tell it the number of hyperparameters you want to look over, right? So this is the number of tuning combinations that will be used. So another way to think about this grid argument is the number of candidate parameter sets to be created. So if we have a grid of 10, it will choose 10 values of neighbors to investigate. And so that can be a data frame, or we can specify it directly. It's like we can say, if we had, for example, 2 hyperparameters, we could use the expand grid function. And we say, okay, we want to investigate a neighbor's value of 1 and 2 and a foo value. So this is just a made up hyperparameter now, values between 3 and 5. And this expand grid function will give you all possible combinations, right? So we have neighbors of 1 and foo of 3, 4, 5, and then neighbors of 2 and 3, 4, 5 for foo. So expand grid can be really useful for calculating all possible combinations if you have set values that you're interested in using for your hyperparameters. All right, so we are going to start by creating a grid of neighbors' values that we want to tune. So use the expand grid function to create a grid of values for neighbors that's going to span from 10 to 20. All right, and we want to save this as K10 underscore 20. All right, so let's take a couple minutes to try and create this grid of values we're going to tune. All right, so we can do this with the expand grid function. So here, because we only have one hyperparameter that we're interested in, we need to specify neighbors. We say we want to start at 10, and this colon says go through 20. So neighbors from 10 to 20. And this gives us a data frame that has neighbors values of 10 through 20. So this is going to be our data frame of candidate values that we're going to investigate. All right, so now we want to make a workflow that tunes over the different possible values of neighbors and uses our normalized recipe. Right? So we'll make a workflow that will need a new model specification, but we can use that same recipe we've been using. And then we want to use tune grid and the CV folds and the candidate values we just created to find the best values of neighbors. So we are going to save the output of TuneGrid as KNN results, and then we can collect the metrics there to see which value is going to be the best. So let's take a few minutes to try and work on this, and then we'll go over the solution together to make sure that we're all on the same page. All right, so let's look at these results. All right, so the first thing that we need to do is create a model specification that can be tuned. So I call this the KNN tuner. Again, you can call it whatever you want, but we specify a nearest neighbor model where the number of neighbors is going to be tuned. All right, so we use that tune function. We set our engine and we set our mode, just like we have been doing for all of our other model specifications. All right, then we can create our workflow. We say we're making a workflow that's going to use this normalized recipe, and we're going to add our KNN tuner model specification that we created. And then we can tune that using the tune grid function. So we take our workflow and we pipe it into tune grid. We say the resamples that we want to use are the CV folds splits that were created in the setup chunk, and the values that we want to evaluate are in this K10 20. So those are the neighbors of 10 to 20 that we created in the last exercise. So we run those results, and then we can collect the metrics from them. And when we do that, we should get something that looks similar to this. Your numbers might be slightly different, but it should be pretty similar. And so we can see for each value of neighbors that we investigated, what the estimated RMSE was of that value. So the value of 10 had an RMSE of 35,817, 11 gave us 35,719, and so on for each value of neighbors. And was everyone able to get tune results that look similar to this? Yes. All right. I will assume yes, but if we need to slow down or go back, please let me know. All right, so once we have these tuned results, we can ask R to show us the best ones. So there is a function called show best, which will find the n best combinations of hyperparameters. And so the way that you use this function is you give it the results of your model tuning, which we saved as KNN results. And we say, excuse me, from these results, show us the best RMSE values, and we want the 5 best. And so if we run that, we'll see that the best value was 16, followed by 17, and then 15, 18, and 19. So from our the values we looked at, 16 neighbors performed the best. We can also use this auto plot function that we've seen a couple of times to look at the results. So if we pipe our results of our tune grid function into auto plot, it will show us for the metrics that we used, which again by default are the RMSE and the R squared. As the number of neighbors increases, the R squared just keeps going up and up and up, but the RMSE does have this curve where we get our lowest RMSE at 16, and then the error starts to increase as we go to more and more neighbors. So in addition to models, we can also tune recipes, right? And so we kind of hinted at this in our last section for principal components analysis. So we're going to return to that example now. So in your exercises, there is a PCA workflow that's already in there for us. And we want to modify that so that instead of specifying the number of components in the step PCA function, we want to tune that value. Right? And there's also a grid of possible values that have been included in your workbook as well. So we want to modify that workflow, fit it using Tune Grid, and then see which values of the number of components give us the best predictions. Right? So again, we'll take a few minutes to work on this one and then come back together. All right, so how can we modify this workflow to tune the number of components? The first thing that we need to do is modify our recipe. So in our step PCA function, instead of specifying the number of components, here we say tune. So we're going to tune the number of components of our PCA. So I've called this recipe our PCA tuner, just to keep it straight on what's happening. And then I can create a tuned workflow. So we create a workflow object, we add our PCA tuner recipe, and then we use our same linear model specification. And when we tuned that, we had 4 different components that we examined in this grid, either 10, 20, 30, or 40 principal components. And so we take our tune workflow, we pipe that into the tune grid function, we specify our CV folds as the resamples, and this number of components 10 to 40 as the grid. And when we look at the results, based on the RMSE, we see that 40 principal components gave us the lowest RMSE of the 4 values that we examined. So does this make sense on how we can tune both model hyperparameters as well as parameters in our recipe? Was everyone able to get results that are at least similar to this? Right. Yeah, I'm going to assume that we're good unless someone tells me not to move on. All right, so let's kind of go back to the beginning of this modeling process. So when we are starting this modeling workflow, we start with our data. We then create this initial split of data into testing and training. Right. And then for our model tuning and model selection processes, we want some resamples so we can assess the error in our models. And so for that, we create, in this case, some v-fold cross-validation of our training data. So again, our testing data is still completely separate. Our resample folds are based on the training data. And so now we have a new recipe that's in your R Markdown document for you. So this recipe, again, is looking at the remote status of employees as our outcome variable, predicted by all other variables. We are creating dummy variables for all of our variables, all of our factor variables that are not outcomes. And then we're using the Lincomb step on all of our predictors. And then we are downsampling in order to correct that class imbalance, right? So this is the same recipe that we saw at the end of the last set of slides on recipes when we talked about downsampling. Okay. And so with this recipe, we can also add a model. So here we specified a random forest model again. So we've used the rand forest function from the Ranger package as our engine in this case. And we can put both of those together into a random forest workflow. So we've created our blank workflow. We add the Stack Overflow recipe we saw on the previous screen, and we add our random forest model specification. And if we use fit resamples on this, again, this is using the default values for random forest, the default mtry and min-in. We can use fit resample with our Stack Overflow folds. And we can see that we get an area under the ROC curve of 0.702. And our question now is, can we do better than that, right? We don't have to use the default values of mtry and min-in. And so let's find values of those hyperparameters that are going to give us better predictions, right? So I want you all to try and do this. And these models can take a little bit of time to run when we're tuning. So that's why I've given you a little bit of extra time here. So if you end up not needing all this time, if it finishes early, please let me know in the chat and we will move on. Otherwise, I'll give you the full 10 minutes. We want to edit the random forest model to tune the mtry and the min-in hyperparameters. Then we'll update our workflow to use that new model specification and tune the workflow on the SO folds splits object. And then finally, we want to use the results from that tuning to find which combination of hyperparameters is going to provide the best area under the ROC curve. And then hopefully what we see is that is going to be an improvement over the default values that we saw earlier. All right. So we'll take some time to do this. And again, if you don't need the full 10 minutes, let me know and we'll move on. All right. Was everyone able to tune this random forest model? So the way that we do this is we are first going to create a new random forest model specification. So we are defining a random forest model, and we say we are going to tune the mtry hyperparameter, and we're going to tune the min-in hyperparameter. And again, we set our engine to Ranger and our mode to classification, since we are predicting either remote or non-remote status. We then can create our workflow. So we can start with that existing random forest workflow and just update the model to be our one that is tuning these two values. And then we pipe that the tune workflow into the tune grid function. And here I'm specifying that I really only care about the area under the ROC curve as our metric. And so notice that we did not specify a grid. We didn't tell it which values we wanted to investigate. And so if you don't specify, the tune grid function will pick some values for you. And so by default, it'll look for 10 combinations of values. And that's why you get this little message that's saying it is basically figuring out which values to try for mtry. And so you can see here we have the 10 combinations that it chose. So we had an mtry of 9 and a min-in of 16, an mtry of 1 and a min-in of 9. So all these different combinations were the ones that the tune grid function selected to investigate. And we see the area under the ROC curve for each of these combinations. And so what you might want to do, if you don't have a good idea of what the mtry or the min-in should be, as you probably realized, it can be fairly expensive in terms of computation time to tune these random forest models. So you don't want to do a whole bunch of them. So what you might do is let the tune grid function pick a few values for you like we did here. And then when we see, it looks like in general, lower values of mtry are going to be better. So like an mtry of 1 gives us 707, an mtry of 7 is 701. And so then we might say, okay, smaller mtry is going to be better. Let's now specify our own values, and we can tune again on those. So you can use this first pass to kind of get a general sense of where those hyperparameters should be, and then you can get more specific and tune again. But that way you're not using like every possible value of mtry, right? Because that's going to take a really long time to fit all of those models. All right, so now that we've tuned our model, what comes next? So the first thing we want to do is find the best combinations. So we can use show best. Again, and it will by default show us the 5 best models or combinations of hyperparameters as measured by the area under the ROC curve. So here we can see that our model with mtry of 1 and min-in of 9 did the best. And so again, if we were doing this for a real analysis, we might want to go back and do some more fine-grained tuning. But for now, for our purposes, we'll just kind of move on with this one as the best. And so we can say, all right, we want to actually pick that as our best model. So there is a function called select best, which will, from your tuned results, select just the one best metric, right? And so if we look at what this SO best object is after we choose our best, it now doesn't have any of the extra information. It doesn't tell us what the ROC for this model was exactly. It just says, all right, here's the best combination of hyperparameters for you. And we can use that to then finalize our workflow. right? Because our workflow still has those tune placeholders in it. And we say, okay, we're done tuning. We now want to finalize our workflow with the hyperparameters that we've chosen. So we can take our workflow and we can use the finalize workflow function. And we're going to finalize it again with those parameters we just identified as the best parameters. So then we have our final Stack Overflow workflow. And then we go back to the test set, right? So we had our original split into the training set and the test set, and we did all of our resampling for tuning on the training set. And so now we can go back to the test set. And so again, this is data that up to now we have not used in any of our model tuning process. And so we can now fit our model and predict it. So we can take our final workflow, again, that's the one we finalized, and we can fit that finalized workflow to our full set of training data. So now we're not fitting it to individual resamples, it's the full set of training data. And we can make our predictions on the test set, which again, we have not used up until now. But this can be annoying, right? To have to fit it and then do like multiple types of prediction. So there is a helper function when we get to the very end of this process called last fit. And so we can take our finalized workflow and we can pipe that into this last fit function. And now instead of specifying that we're going to fit the model to our training data and then predict on our testing data, we just give it that initial split object, right? And it will automatically do the fitting to the training data and the predicting on the testing data. And so when we use the last fit function, we get a data frame back. So again, it's going to have our split. Was our initial testing and training split. It's going to give us our final metrics for the model, any notes if there were problems with the estimation, predictions for our test set. So what predictions did we make? And finally, there's a workflow column, which is going to include information about our workflow, including our final fitted model. All right. And so just like we could when we use the normal fit function, we can take the results of this and use the collect metrics or the collect prediction functions to get the metrics and predictions out of here and see what our final performance looks like. All right, so let's try this. We are going to use select best and finalize workflow and last fit on the random forest tuning that we just did. And we're going to take the best combination of hyperparameters and use them to predict the test set, right? And then the last thing we'll do is look at how the area under the ROC from our test set actually compares to our cross-validated estimate that we got when we were doing our model tuning. Okay, so let's take a few minutes to fit this last model, and then we'll look at how our performance compares. All right. So let's look at how we can get our final set of results. So the first thing we do is we select our best set of hyperparameters. So again, we take the results of our tuning process and use the select best function. And we're going to select the best based on the ROC AUC metric. If you wanted to use a different metric to choose your best set of hyperparameters, you could do that by specifying that here, but we'll use the ROC. Then we will finalize our workflow using those selected hyperparameters, using the finalize workflow function. And then finally, we can do our last fit with the last fit function. So we take our finalized workflow, we pipe that directly into the last fit function, and we give it our initial set of splits, which were the initial training and testing set. And that'll give us our final fitted model. And so we can collect the metrics from that. And we see that the accuracy of our predictions on our test set was 0.634, and the area under our ROC curve was 0.661. Was everyone able to get results that are similar to this? Thumbs up, awesome. All right, so now let's compare the performance. So when we were doing our model tuning, and we picked our values of 1 and 9, we saw that we had an estimated area under the ROC curve of 0.707. So that's what we would expect our area under the ROC curve to be in our testing set. But when we did our testing set, we saw that we got an ROC of 0.661. So in an ideal scenario, the performance from resampling should be similar to what it is in the test set. If it is higher, as is the case here, then we may have a little bit of concerns about overfitting, right? Our performance on unseen data is not as good as we were hoping it would be, but it's pretty close, so it may not be that much of a concern in this particular case. But that is something to keep an eye on when you're fitting your own models, is not just looking at what your final performance is, but how does that performance compare to what you were expecting it to be? All right. So now we get into all of our final looks at our model. So we can get, again, our final metrics by using the collect metrics function from our results of that last fit function. We can also get the predictions that were made on the testing set by using the collect prediction function. And so again, we have the probability that each observation in our testing set was remote or not remote, as well as the predicted class and the truth. So this remote column is what the observed remote status was. And we can also calculate our final ROC curve, right? So we have, again, the results from our last fit function. We can collect those predictions and then use the ROC curve function to create that data frame that has all the information we need. And the auto plot function, again, will plot our ROC curve. And so you see this looks okay. We're above the diagonal, which is good. That's where we want to be. But we're not like super far up here in the corner either. So we're doing an okay job of predicting, but not great. Right. So does anyone have any questions about model tuning, how we go about figuring out what our best hyperparameters are going to be and then applying those to our original data? We're going to get to practice this again in our next set of slides, which is going to be our final case study. And so that is going to take all of the modeling stuff that we've learned so far and wrap that up into a single analysis. So we'll get to play with all of the packages we've learned and see how they all fit together on one problem. right, I'm not seeing any questions, so I'm going to go ahead and switch over to our next slide deck. All right. And this is actually our second to last slide deck. So depending on how long it takes us to get through this case study, we may actually end a little bit early today, get everyone to the weekend, hopefully a little early. All right. All right. So let's go ahead and get started on our case study. We'll see how far we get before lunch. So as was the case with our first case study, we're now going to combine all of the stuff that we've been doing so far with our modeling packages into one data analysis that will hopefully help illustrate how all of these different packages fit together and create your modeling pipeline that's going to help you going forward. All right, so let's go ahead and start by opening our last set of exercises. It's going to be case study 2 in your exercises folder, and run the setup chunk. All right. All right, so I'm going to start by going through our process for modeling. So this is kind of like an overview of the process we're going to go through in a process that hopefully will be applicable to the future modeling work that you all are doing, right? So we start with our original data set. And from our original data set, we then split it, right? We split it into a training set and a testing set. And the training set is what we're going to use for our model tuning, model selection. Basically, as we iterate through different options, we want to only use our training data so that our testing data stays like pure and unaffected by what we're doing. So we take our training data and we split it into multiple resamples, and that could be through bootstrap sampling or cross-validation. However we want to resample our data. And then for each of those resamples, we are going to fit a recipe. So we'll train our preprocessor, we'll fit a model, and those can be combined into a workflow. And as we fit that workflow to each of the resamples in our data, we get some metrics out. That's going to help determine which hyperparameters we use, and if we're comparing multiple types of models, which model we want to use going forward. And so after this process, we make a final decision on what our model we're going to use, the hyperparameters that we've selected, and we end up with that one single trained workflow at the end. We then, and only then, will use our testing data with our trained workflow to get our final set of predictions and our final set of metrics. Right? So this is like the high-level overview of the modeling process that we should be going through, right? And so with tidy models, we've learned about a bunch of packages that help with different parts of this workflow, right? So we use the rsample package to create that initial split of data. We use the rsample package again to create our resamples, so that's bootstrapping or cross-validation. We then can use the recipes package for creating our data pre-processing and the parsnip package for defining our models. And then we wrap both of those up together into a workflow. As we are applying that workflow to each of the resamples, we collect metrics, which come from the yardstick package. And then as we just talked about, we use the tune package along with the metrics to figure out which set of hyperparameters is going to be the best for us. We then can finalize our workflow to get our final workflow. And again, we assess the final metrics with the yardstick package, and we can then look at which variables are important using the VIP package. Okay. So this is the process we're going to go through and how all of these different packages that we've talked about fit into this process. All right, so the data that we're going to use for this case study is a new data set that we haven't worked with yet, but it's about hotel bookings. The data come from this paper, which is in your, I believe, the references folder in your project. If you're interested in the paper, we are using a slightly modified version of this data set that includes only hotel stays. So instances where the people actually showed up for their hotel stay. So like if someone booked a hotel but then canceled their stay, we're not including that data in this analysis. And so what we want to do is try and predict which hotel stays included children and or babies. And we're going to be using two different methods to try and evaluate this. We're going to use a logistic regression model and a random forest model, right? And we'll try and pick which one's going to give us the best predictions. So here is a glimpse of our data. You can see that we have 50,000 rows. We have 50,000 observations in total, and we have 23 columns. So this includes the type of hotel, how far in advance the booking was made, whether the stay was in weekend nights or weeknights, whether there were adults, whether there were children. So that's going to be our variable that we're predicting, whether there were children or not. And then a bunch of other variables about this hotel stay. Right? So to start, I want you all to look at our outcome variable children in the hotels data and see what levels are there and what proportion of cases are in each level. Right? So we'll take a few minutes to work on this, and then we'll make sure that we all agree. All right, so let's take a look at this data. If we have the hotel's data, we can use the count function to count the number of cases in each level of children. So we see that there are two levels to this variable. There are either children or none. And we see that there is a quite large class imbalance here. So of the 50,000 rows in our data, almost 46,000 had no children and only 4,000 did have children. So about 92% to 8%. And so with a class imbalance this large, we might want to consider either upsampling or downsampling. But for now, 4,000 is still a pretty good sample size of cases. So we'll go ahead and use the data as it is for now. But that's one of those places where as we start to fit models, if we see that we're not getting very good predictions, and we might want to come back and add some upsampling or downsampling. But for now, we'll leave it as is. All right. So the first thing we want to do, that very first step in our flow chart, is to create an initial split of our data by creating a training and testing set. All right, and we want to call this splits, right? But because there is a class imbalance, we're not going to upsample or downsample, but we do want to make sure that we stratify our splits by that outcome variable so that we at least know that cases with children will be represented in both the testing and the training set. And so once we create that splits object, we're going to extract the training data as hotel other and the testing data as hotel test, right? And if you can keep set seed 1, 2, 3 in your code, that will hopefully result in all of us getting the same results. But if not, our results should at least be similar. All right, so let's take a few minutes to create those splits objects, and then we'll keep moving through our case study here. All right, so let's make these splits. All right, so first I'm going to set my seed to 1, 2, 3, so that this will all be reproducible. And I create this initial set of splits using the initial split function. So I'm going to split the hotels data, and I'm going to stratify based on that children, our outcome variable. And if we look at the splits, we again see that we have 50,000 total cases in our data. 37,500 have been put in our training set, and the other 12,500 are going to be in our testing set. And so we can extract those using the training and the testing function. So the training function will pull out our training data into this hotel other, and the testing function pulls out our testing data into hotel test. And so if we look at those, we can see that the proportion of children is about the same in both our testing data up here, or the training data up here at the top. So we can see about 8% of our data were children. And in our testing data, again, we have about 8% of the data were positive for children. So our stratifying worked, and we have about equal proportions in both the training data and the testing data. All right, so the next thing we want to do is create some resampling of our training data that we can use for model tuning and model selection. So we will use tenfold cross-validation for this. And again, we want to stratify by children in order to make sure that all of our resamples have about the same proportion of cases with children in them. So let's take a couple minutes to create a cross-validation of our training data, and we'll call that folds. All right. So we can do this with our vfold CV function. So again, I've set a seed here just to make sure that I will always get the same results on my computer when I run this. But we are going to create a vfold cross-validation, again, just of our training data, which we put in hotel other, and we specify 10 folds, and we are again stratifying by children. And so if we look at those folds, we see that each one of these has 33,750 in the analysis set and 3,750 in the assessment set. So when we do our model tuning, it'll be fitting the model to this section and then using these 3,750 to estimate the performance with our metrics. Right? And so these numbers are the same for each of our splits, but it's a different testing set each time. All right, so let's look at our first model. So we have two models that we're going to fit and compare. Let's see which one's going to perform the best for us. The first one is going to be a penalized logistic regression. And so we can estimate this in R using the GLIMNet or GLMNet package. And in this penalized logistic regression model, a penalty is applied to slope parameters. And what that does is it pulls those coefficients towards 0 if the predictor is less relevant, right? So if you're not providing a lot of information, we're going to add a penalty. But what size should that penalty be, right? That's not exactly clear. And so we're going to do some tuning to figure out the optimal penalty size. Okay, so we want to first build a model specification for the penalized logistic regression model. We'll call that LR mod. And in the specification, we want to define the model so that the penalty parameter can be tuned. Okay? And we will use GLMNet as the model engine. All right, so we'll take a couple minutes to make that model specification. All right, so let's take a look at this model specification. So we will call it LR mod, and we're doing a logistic regression. So again, this is going to be the logistic reg function. We are going to tune the penalty value. And here we've set the mixture to 1. And all this means is that our model has the option to potentially completely remove irrelevant predictors and choose a simpler model if it wants to. But we're going to tune that penalty value, and we're going to set the engine as GLMNet. We could also set the mode to be classification if we wanted to, but logistic regression can only be used for classification. Right? So that's why we don't have to set it. All right, so the last thing we'll do before lunch is create our recipe for this model. So we'll go through this process and then we will break for lunch before we actually fit it. So as we are creating our recipe, we might think about date-based predictors that could be useful related to the arrival date, right? So we might expect, for example, summer months to be more likely to have children because they're on summer vacation, right? Or maybe around Christmas time if parents are going on trips over Christmas break. So these are things that we might want to extract as features from our data. So we might want the year, month, or day. We might want some holidays to code those. And so we can add these to our recipe as part of our feature engineering. So we want some date-based predictors. There is a step date function that will pull out the year, month, and day variables. There is step holiday, which will code whether dates are holidays or not. And then we want to do some of the pre-processing steps that we do for a lot of our models, right? We want to convert all of our factors to dummy-coded variables. We want to remove any variables that have only one value, so they have 0 variance. And then the last thing we want to do is center and scale our numeric variables. All right, so this will be our last exercise before lunch. I've given you all a list of holidays in the notebook already. So we want to create a recipe called LR recipe that is first going to create year, month, and day variables from arrival date, and then create holiday indicators based on the arrival date. And then once we do that, we can remove the arrival date variable, right? Because that's going to be redundant once we've calculated these other features from that variable. And once we do that, excuse me, we'll create the dummy variables and remove variables that have only one value. Okay. And again, you can do question mark step date or question mark step holiday if you have questions about how those functions work. All right, but let's take a few minutes and then we'll go through the solution before lunch. All right, so let's look at this recipe. So here is the list of holidays that were identified for this analysis. So we'll use that in the step holiday function. So we start by creating our recipe. So we're going to predict children from all other variables in our data set. And again, we're using the hotel other, our training data, as the template to figure out what type of variable each one is. So the first thing we do is we call step date on the arrival date, step holiday, again on the arrival date, and we specify our set of holidays, which again were specified up here. We can then use step RM, that's step remove, to remove that arrival date column. So again, there are a lot of different step functions we can use. We've only looked at a few of them this week. Then we create our dummy variables from all of our factor variables, excluding our outcomes. We remove any predictors that have 0 variance. And finally, we center and scale. So you could do this as 2 steps. You could do step center and step scale. Step normalize is just a shortcut that will do both of those at once for you. So I've normalized all of our predictors. All right. So that is our recipe. We will now go ahead and break for lunch. And when we come back at 1:30 Central Time, we will put this into a workflow and start tuning our logistic regression model. All right. So we'll be back at 1:30 p.m. Central Time. All right, welcome back. I hope everyone had a good lunch. All right, we are ready to go through our last afternoon together. So all we have left is this case study that we'll keep working through, and then one last set of slides to just kind of wrap up the week together. All right, so before we left for lunch, the last thing we did was create this recipe that we will use for our penalized logistic regression model. And so what we want to do now is take a couple minutes to create our workflow. All right, so we've created our model specification, we've created our recipe. So now we're gonna take a couple minutes, make a workflow, and then we'll start fitting some models. All right, so this workflow looks like all the other workflows we've put together so far. We first just initialize our empty workflow. Then we're going to add our logistic regression model, and then we add our recipe that we created, right? So that'll be the workflow that we will start tuning. So now we're going to do that tuning. So we want to tune the logistic regression workflow, and I have provided a grid of parameter values that we'll tune over. So after you tune, look at which penalty value provides the best area under the ROC curve. And then also create a plot that shows the penalty value on the x-axis and the area under the ROC curve on the y-axis. All right, so we'll take a few minutes to work on this one. All right, so let's take a look at these tuning results. So first we have our grid of possible penalty values that we're going to examine. So this is creating a sequence from -4 to -1, and we want 30, so it'll give us 30 numbers evenly spaced between -4 and -1. So these are the possible penalty values that we will tune over. To do the tuning, again, we pass our workflow object into the tune grid function. We give it the folds that we created, our resampling folds of the training data. The grid of values, again, is this LR reg grid. And we're also going to tell it to save the predictions. So we can look at those if we want to. And because we're only interested in the area under the ROC curve, I'm only returning that metric. And so after, excuse me, after the tuning is done, we can look at the best performing penalty values, and we get this list here. But what we see is that they all have like right about the same performance, right? They all have an area under the ROC curve of 0.875. And if we create a plot, so again, we can collect the metrics and make a ggplot with code that hopefully looks familiar. And we get a plot that looks like this. And so we can see for all of these lower penalty values, we get basically the same performance, right? There's kind of a plateau. And as we keep increasing the penalty value, then performance starts to drop, right? And as we get to the largest penalty value, where we're basically removing all of the predictors, then it's basically a 50-50 shot of whether we're getting our predictions correct or not. And so if we look at our top models, we can arrange them to look by our penalty value. So again, here we have our smallest penalty going up to larger penalties. And so we can see that performance changes a little bit. So that plateau isn't perfectly flat. It is increasing a little bit. And then it starts to drop off a little bit. But all of these 15 values have essentially the same performance, right? So which one do we actually want to use? So the best value, if we just used select best, would be this penalty value of 0.00137. And if we look at our plot again, that is this value on the plateau. So like we're close to the edge, but not really. And so what we might do is we might choose a different penalty value that's further along the x-axis, closer to where we start to see that decline in model performance. So for example, model 14 here, if it's the 14th penalty value, and that's a penalty value of 0.0022, has effectively the same performance as the numerically best model. But this one might eliminate more predictors, right? And so it might give us a more parsimonious model and help prevent overfitting, right? And so in general, fewer irrelevant predictors is going to be better. And so if performance is going to be the same, we'd prefer a slightly higher penalty value. So we're going to go ahead and select this solid line as our penalty value that we want to keep and use as our final hyperparameter. And so we can pull that one out specifically. So instead of using select best, we can select a different value. And so here we did the model 13, the 13th value, which I thought we were picking the 14th, but I guess we chose the 13th. So this graph and the one we picked are actually a little bit different. So the slides will use the 13th penalty value as the one that went into the logistic regression as our final value. Does that make sense? Why we might not always just go with whichever one had the numerically best output? Yes, good. All right, so let's go ahead and finalize this workflow. So we want to look at our ROC curve for our selected penalty value. So we'll use collect predictions, and we can do that because in our model fitting, we used this control statement to save our predictions. We use this save pred. And so now we can use collect predictions on those results. And if we specify that parameters equal LR best, that will give us only the predictions for our selected penalty value. And once we have those predictions, we can pass that to the ROC curve function to make the data for the curve. And then we can make the ROC curve either using autoplot or with ggplot. And after we make this data frame, we'll add one additional variable called model that has the value logistic regression. So we'll use mutate to do that. And that'll be useful later on when we compare ROC curves from multiple models. Right? So let's take a few minutes to try and make this ROC curve. All right, let's check out this ROC curve. So we take our tuned results and we can collect predictions. And again, set our parameters to LR best, which is what we saved our selected hyperparameter as. We then pass that to the ROC curve function, and we tell it that the true results are in this children variable. The estimate is then the probability that a certain hotel booking included children, and that is in this pred children column. And finally, we add a variable with mutate called model, and that's just always going to be equal to logistic regression, right? And we'll see why we want to do that a few slides from now. And so once we have that, we can use autoplot. And we see we have a pretty good ROC curve here. Right? Our area under the curve is 0.875, so that's pretty good. It's above that 0.8 threshold that's used as a little bit of a guideline. But we might be able to do better with a different model, right? So now we're going to fit a random forest, and we'll see if the random forest can outperform our logistic regression model. So for the random forest, there are several packages we could use. Two that we've used so far in this course are Ranger and RPart, but we'll use the Ranger package here. The random forest is going to be more flexible than our logistic regression. And again, this is an ensemble of many decision tree models. So the first thing we'll do is, again, build that model specification. And we can call it RF mod. And we want to define this model so that we can tune the mtry and min-in parameters. Again, we're going to use Ranger as the model engine. And remember, we will need to set the mode for this model because the random forest can do both regression and classification. Right, so we'll take a couple minutes to make this model specification. All right, let's check out this model specification. So we have our random forest model. So rand forest, we are going to tune the mtry and the min-in parameters. And here we've set the number of trees that are going to be ensembled to 1,000. We set the engine to Ranger. And because we're doing a classification problem, so whether it's children or no children, here we set the mode to classification. The next step, again, is to build our recipe. So this will look very similar to our logistic regression recipe, except that random forests do not require dummy coding or normalized predictors that are often helpful for a logistic regression or a linear regression, right? So the random forest can kind of just handle things as they are, but we'll still want our date-based features. So we'll use the same list of holidays, but we'll create a new random forest recipe that's going to have 3 steps. We will create the year, month, and day variables from arrival date. Then we'll want our holiday indicators. And then finally, we can remove that arrival date again, since it's redundant once the other 2 steps are added. Helps if I unmute myself. To create this recipe, it's going to look just like the other recipe that we made. So we start with our call to the recipe function. Again, predicting children from all other variables. And again, using that training data as our template to identify the types for each variable. And then we have these same 3 steps that we used for our logistic regression model. We use step date, step holiday with our set of holidays specified. And then finally, we can use step RM to remove that arrival date. All right, and our last sort of preparation step is to create that workflow object. So we'll take a couple minutes, create a workflow of our random forest model specification and the recipe we just created. All right, so to get our workflow, we just define, we initialize it with that workflow function, add our random forest model, and then finally add our random forest recipe. And that's our workflow that is ready to tune. All right, so the next step is to tune our workflow, but I will just warn you, you do not want to do this on your computer unless you are prepared to wait. So tuning this random forest workflow takes a long time, like more than an hour. So if you start running it, you're going to be waiting for a while before you can do anything else in your R session. All right, and we'll talk about why it's taking so long. One reason is that random forest models are just more complicated, so they're more computationally expensive to run. And we're also fitting a lot of them. Right, so in the code, and I've included this code in your notebook, so you can run it if you want to, just be warned that it will take some time. So we specify a grid of 25 values. Here, we aren't specifying which 25 values, we're gonna let Tune pick them for us. But that's 25 combinations, and we have 10 folds. So we did 10-fold cross-validation. So it's fitting 250 random forest models. And then each random forest model, remember we specified 1,000 trees. So really what's happening is that we are fitting, if I can do my math real fast, 250,000 decision tree models. So that's a lot. And then it has to aggregate those for each random forest model. So there's a lot that's going on here, even though this is like not very much code, right? Only a few lines of code, but we're fitting 250,000 decision trees with it, right? So like tidy models is very powerful. Like the fact that we can do that in such short code is like really kind of incredible. But be aware that some of these times when you go to tune your model, it may take quite a while depending on the amount of complexity that you have. So I went ahead and ran this and I saved the output. So you have the output in your project folder. So if you run this code, which I believe is in your notebook, you will get this RF-res output. So it will be as if you had run this, but you don't actually have to run it and wait the hour for it to finish. Again, if you want to do that, feel free, but I would recommend waiting at least until we are done so that your R session is available for the rest of these exercises. All right, so now that we have those results, let's figure out which mtry and min-in values are going to give us the best area under the ROC curve. Right? So take a couple minutes to look at those results and see which combination is going to be the best. All right. So again, we have the code that's used to tune the model, which we already talked about. So these are our results. If we look at show best, you'll see which ones are the best performing models. We see that the combination of an M-try of 7 and a min-n of 11 is numerically our best with an area under the ROC curve of 0.925. And we can look at a plot of this. And so we can see, so this is the number of randomly selected predictors. That's our M-try. It appears that lower values tend to be higher. We can see it start to decrease as we do higher M-try values. And similarly for min-n, it appears that lower values are on average a little bit better. But also keep in mind that for the scale of our axis here, almost all of these models, except for one, have an area under the ROC curve of greater than 0.91, right? So they're all performing pretty similarly to each other. All right. And so since they're all basically performing the same, we'll just use select best. And so we can do that with the select best function. And it will give us our selected hyperparameters of 7 for M-try and 11 for min-n. And again, if our random seeds are different, you might end up with slightly different values than I do. But we should not for this one because we're all using that same output that I provided. All right, so now let's calculate our ROC curve for this random forest model. So we're going to do this the exact same way we did it for the logistic regression model. We can collect predictions by setting the parameters to RF best. That'll give us just the predictions from our selected hyperparameters. We can use those to create our ROC curve with the ROC function. And then finally, again, we'll add that extra variable. This has random forest. That'll help us compare our ROC curves in our next exercise. All right, so we're going to do this the same way we did for the logistic regression model. And we take our results and collect predictions. And again, by setting that parameters equal to RF best, we'll only get the predictions back for that combination of hyperparameters. We then use the ROC curve function to calculate the needed information for our ROC curve, again, with that same truth and estimate specification. And now we add our same model variable, but this time it's equal to random forest. And so if we use autoplot to create a plot of this, we see our ROC curve here, right? And it's pulled up a little further to the left, that top left corner, right? So this is looking pretty good. All right, so now we have tuned a linear regression model. We've tuned a random forest model. We've looked at their metrics. And what we want to do now is pick like which model is going to be our final model. So like if we were at a company, we'd be saying, okay, which model do we want to put into production, right? So we need to compare the logistic regression model to our random forest model, right? And to do that, we're going to compare the area under the ROC curve from each of our models. So our final logistic regression model and our final random forest model. So we'll do this in two ways. The first is just by looking at the area under the ROC curve for each of those. So just that one number summary. And then the second method is going to be to plot both of our ROC curves together, right? And by doing that, we can look and see if one is uniformly better than the other. And we can use that to decide which model we should select as our final model. So let's take a couple minutes to compare those models, and then we will make our decision. All right, so let's compare these models. The first thing we can do is look at those single number summaries. So we see that the logistic regression model had an area under the ROC curve of 0.875 compared to 0.925 for the random forest model. So by that measure, we would say that the random forest model is the best. And we can also use ggplot to look at both of those curves together. So this is why we wanted to add that extra model variable. We can color by the model. So we'll get two separate lines, one for logistic regression, one for the random forest. Right? And so if we look at that plot, we see that the random forest model is in this kind of burnt orange color. Logistic regression is in the blue. And we can see that the random forest model is uniformly better than a logistic regression model, right? It's always above it. So based on this, we would pick the random forest model to be like our final model that we want to move forward with. Okay, so now that we've picked the random forest model, like now what? What do we do? So this is where we are at in our like modeling pipeline, and we've reached that trained workflow state. Right? We have compared models and tuned them, and now we have our final random forest model that we've selected and found the optimal hyperparameters for. And so the next step is to use our testing data to get predictions and our final metrics, right? To make sure that the model is going to perform as we expect it to. So what we want to do now is create a new random forest model specification, but instead of using tune for mtrain min in, we want to specify our selected hyperparameters. And we'll still use the Ranger engine, but now we want to add importance. We want to look at variable importance of our final model. So we'll add importance as impurity. And then we can create a new workflow that takes our original workflow, but then updates with this new model specification. Right? So let's take a couple minutes to make our final random forest workflow. All right. So to refresh ourselves, we can look at that RF best object and see that our selected hyperparameters were 7 for mtry and 11 for the min-in. And so we can create this new model specification. We do a random forest model. We set mtry to 7, min-in to 11. We keep our same 1,000 trees. For our engine, we again use Ranger, but set the importance to impurity so that we can look at a variable importance plot. And then finally, we set our mode to classification. And then we can take our random forest workflow, the one that we used for tuning, and we can just update that with our new model specification. So now we have our final random forest workflow. All right, so this is our last exercise. And we want to take our final workflow. We want to fit that random forest model to our entire training set, and then use the predictions from the test set to find the area under the ROC curve for our final model. All right, so it'll take a few minutes to work on that and get our final results. All right, so let's take a look at our final model. So we take our last workflow that we just created, and we can pipe that directly into the last fit function. And we tell it we want to fit this workflow on that initial splits object that we created at the very, very beginning that made our training set and our testing set. And so that'll fit this workflow to our full training set and then predict on our test set, which to this point we have not used. And so we see our final metrics. We have an accuracy of 0.945 and an area under the curve of 0.923. And so we can take some final looks at our model. We can again do that performance comparison. So we can look at the ROC from when we were tuning. So our estimated performance was 0.925. Our final performance on our testing set was 0.923. So those are right about what we would expect. In our ideal world, our test set performance is almost identical to what we got from our cross-validation, which is good. And we can also make our final ROC curve. And here is some code that will first calculate the data for our ROC curve and then add it to our previous graph that we made. So again, we can see logistic regression again in this bright blue. The random forest from our tuning, so the model we selected is in a light pink that you can't really see because our final model in the dark pink is almost right on top of it. Okay, so our performance from our final model is almost identical to what we would have expected and hoped to see based on our tuning results. Right? So this is all good stuff. And finally, we can look at our variable importance plot. So to get this, we pluck our fitted model out of the workflow column. So if you look at just the last RF fit, you'll see that dot workflow column on the end. So if we pull out our fitted model, we can look at our variable importance, and we can see what variables are having the most impact on our predictions. So we can see the type of room, the daily rate, and the assigned room type and lead time. So that's planning are the most predictive of whether the hotel stay is going to have children or not. And so that's our case study. We did that full modeling from the very beginning, splitting that data, tuning, and selecting multiple models, and then finally fitting that final model to check our performance. Does anyone have any questions about this process or any of the steps that we went through? And I will also ask, just kind of checking in with everyone, we do have one final slide deck that's not going to take us too long to get through. It's just a wrap up of everything we've done so far. So we are at our normal break time. Do we want to take a break for 15 minutes and come back, or we can also just power through and get out of here a little early? All right, so we will go ahead and just switch to our final slide deck. So we can all say hi to Larry one more time. All right. All right, so thank you all first for making it through this entire week. I know it is long and a lot of content and not a lot of time. So just to recap what all we went through this week. So we started with this applied data science flowchart that we saw a lot at the beginning. So we talked about importing data, tidying it, going through this iterative cycle of visualizing our data, doing some modeling, transforming, and going through this. We did not talk a lot about communicating, but you all have been exposed to some of those things, maybe just without realizing it. So the packages that do this that we talked about were readr for importing, tidyr for the tidying, dply or ggplot, and then the whole tidy models ecosystem for that modeling part. We briefly talked about per to help us program and do a lot of iteration quickly. And then we did not talk explicitly about R Markdown for communication, but you all have been using R Markdown all week in your exercises. So hopefully, if you go looking for R Markdown resources, things will seem familiar, just kind of by osmosis as you've gone through this week. And I will give you at the end of this slide deck some resources if you're interested in learning more about R Markdown for communication. And so then in the second half of the week, we talked about modeling. And so we built up this rather complicated flow chart with a bunch of different pieces for how to go through a modeling process. And we just went through one from beginning to end on our hotels data. And along the way, we learned about a bunch of different R packages. So we did R sample for model splitting, recipes, parsnip, and workflows for building out modeling pipelines, tune for tuning our hyperparameters, yardstick for getting model metrics, and then finally the VIP package to look at variable importance plots. And so we've done a lot of packages this week. Not all of them were on those last 2 pages, and not all of them are here. There are additional ones. And there are a few on the bottom that, again, we have not really talked about, but you've maybe been exposed to them without realizing it, right? So we had the R Markdown package, which is where your exercises were. The sharing again package, we did not use explicitly, but all of the slides that you've seen this week are written with this package. So they're written in R Markdown, and this package makes them into nice slides. And so if you go into our project directory, I mentioned at the beginning of the week, there's this site folder that has all of the website materials. If you go into site, static, and slides, you can see the R Markdown file that built all of these slides decks. For example, if we pull up 16 wrap up, this is the R Markdown code that built the current slide deck that we're looking at. And there's one, I forgot, the blog down package. Again, it turns our Markdown documents into websites. And so that's what our course website was built with, was the blog down package. And the last one down there is RepRex. And that's one that I want to talk about very briefly right now, because that will be helpful after this course, right? And so the RepRex package is used to get help. Right, and so we've covered a lot of content this week, but we have only scratched the surface of what R and the tidyverse and tidy models can do. And so I want to make sure that as you all continue to program in R, you have tools to get help along the way, because you will have questions. We all have questions. Like, I still use the RepRex package all the time to ask questions. And so the goal of the RepRex package is to help the people you're asking the question to help you, right? And the way we do this is by creating a reproducible example. And that's where the term RepRex comes from, a reproducible example. And so the goal of a RepRex is to create the simplest example possible to illustrate the problem that you're having that anyone else can run on their own machine. So we don't want to use data that's stored on your computer, because other people won't have that. And we don't want to assume that the options I've set are the same options that you would have set, right? We saw this earlier in the week when I had the scientific notation option slightly different than some of you had set on your own machines. And so RepRex is going to help us with this. And so I might have a question that I want to sort by a sum and then all component columns. right? And so if I just asked you this question, I was like, hey, I have this R problem, how do I do it? Like, you might understandably like be very confused and say like, I don't know what that means, right? And so we need to give more details than just the question. Right? And so for my specific use case, what I'm doing is I have some data that has like a student ID, and it lists these different skills that the student may or may not possess, right? And sometimes there's 3 skills, sometimes there are 4 skills. It could change. And so what I want to do is I want a solution that will allow me to sort this data frame by the total number of skills and then by each component skill, right? So if 2 students have mastered 2 skills, sort by skill 1 first, then skill 2, and then skill 3 as a tiebreaker. Right? And so I want a solution that'll work no matter how many skills there are. And so I could write this question now, maybe a little better. I say I want to sort this data frame by the total skills and then by each component skill, and I give this example data set. All right, so this is better, but not great, right? If I send you this, I can send you this question and this data frame, but you don't have this data on your computer, right? Like in theory, you could like try and copy and paste this out, but that is annoying and time consuming. And if I'm asking you this question, like I want to make it as easy on you as possible, right? I don't want you to have a whole lot of friction. I want you to be able to help me relatively quickly. So this is where our reproducible example comes in. And we're going to give just like some example data that anyone can run on their machine. So I say, okay, here is some data. I'm just going to make 5 students. So I'll make their IDs 1 through 5. I'll make up some 1s and 0s for whether they possess each of these skills. And so here's some example data that if I send this to someone, they can just copy and paste this and be ready to go to help me find a solution. So bad is just asking a question without context. Better is asking a more detailed question with maybe like some data but not usable. And then the best is going to be to provide an example of what you want, including that better question and some solutions you've tried. And so I can say like, here's what I want. Like if I have 3 skills, I can do this manually, right? I can calculate a total. I can sort by the total and then by each of these skills descending. So I can say, I want this, but I want to do it without having to specify these skills individually, right? So then it's clear to the person I'm asking what it is exactly that I want. And I can say, here's something I've tried. It's like I've tried to sum across anything that starts with skill and then sort by anything that starts with skill, but I get this error, right? So like I've tried to make this work, I can't figure it out. Like, what do I do? And so to ask a good question, you want to give a brief description of what you're doing, your reproducible data, what you've tried, what you've gotten, and then what you want to get, right? So if you include all of these things, you're much more likely, 1, to have someone answer your question, and 2, to get a response and a solution that actually work well. And so RepRex is going to do these middle 3 things for you pretty easily. So the RepRex function from the RepRex package will run code, format it, and render it to your clipboard so you can paste it on whatever online forum you're asking your question at, right? Or you could also drop it into Slack if you use Slack. So X is the code, and this will by default look on your clipboard. So you can copy some code and then run RepRex and it'll make it for you. And I'll give you an example of this just shortly. You specify your venue where your question is being posted. So that could be the RStudio community page, which I'll show you in just a second. It could be Stack Overflow, could be Slack, whatever venue you are using. And then you can add some extra options, for example, whether to include session info. This includes your R session, your package versions, operating system, which can sometimes help people understand why your code isn't working. And then this style option will say whether to format your code nicely, right? And so we'll look at a very quick demo that I've put together and based on the same example we were talking about. Although it appears that my R window is frozen. Well, that's not what we like to see. So we will quit RStudio and we will try again. All right. So in this R script 16 wrap up, I added this after the course started. So if you don't have it in your project, you can always re-download the zip file, or you can just download that one file. But so the way RepRex works is I've added like some narrative text describing my problem, right, and what I want to happen. I've included, here's my reproducible data. I have some more narrative text here that says like I can sort this manually, but I don't want to hard code them. Basically walking through the problem and then what I have tried to do so far. And then this is what's going to give me the error, right? And so if I highlight all of this and copy it, I can then use the reprex package and the reprex function, and I'll just accept the defaults. So if I run this, it'll say it's rendering this reprex. And here it is. It will show in this viewer. So again, we have the text. It'll have the code that's formatted nicely. Again, and then it'll show that error that happens. And so then I can go post this somewhere. So there are a couple options for posting these. One is Stack Overflow. And so the reprex goes to your clipboard automatically. So I can go to Stack Overflow and say I want to ask a question. And then I can just paste that here. And my question, if we look at this preview, is now ready to go, right? It's just automatically formatted, looking nice. And anyone can get in here and copy this and be ready to run it on their own computer to try and help troubleshoot. Another option is the RStudio community page. And I have links to these in the slides as well, where again, I can ask a new question. And if I paste this, again, I get a nicely formatted question that's easy for people to read and understand what's going on. So as you run into questions and you're looking for help, I would highly encourage you to use the reprex package to help build out those examples so that people can understand what it is that's going wrong and what it is that you are hoping to achieve. And so just in case you're curious, here is the answer. It's not super important, but it felt wrong to not include the answer and just leave the question open. So there are a few places to ask for help online, and they have different reputations and different things they are good at. So Stack Overflow is one that we just looked at. It's good because you can post your reprex there, and it also has searchable solutions. So you might go to Stack Overflow and find that someone else has already asked your same question. So you might find a solution without even asking, but it can be a little intimidating to post there. Another place you can go is Twitter. So there's an rstats hashtag that's pretty active. You can't really post a reprex on Twitter because they're usually much longer than however long tweets can be. But they're good for quick questions and you can usually get some pretty quick responses. The RStudio community page is my preference. You can post your rep recs there, as we saw. You get some really good discussion. Also, if you're using the tidyverse and tidy models packages, most of those package developers, the people who make them, all work at RStudio. So you can often get help from the people who create the packages, and they're super friendly. So I would highly recommend the RStudio community. And finally, there is Slack, and specifically there's an R-Ladies Slack channel, which is also super friendly, where you can post rep rexes and get some good discussion. So some final resources for rep rexes. Here's the link to the RStudio community page, along with a post on how to write rep rexes, so you can get additional information there. Again, the link to Stack Overflow, and another post on the Stack Overflow page about how to make a really good reproducible example. And finally, there's the Tidyverse blog, and they have a section on getting help, which is also very useful. And also, don't underrate the power of Google. So I find this tweet to be very accurate. So being good at coding really just means being really good at Googling. I spend a lot of my time on Google figuring out or finding people who have already found solutions to the problems that I'm having. All right, so what's next now that we have finished this week-long course? The next few slides are basically just a resource dump of anything you might want to learn. So if you're interested in doing more data science things with R, all of these books that I'm going to show you are available for free online. So you can just click on any of them. It'll pop up that book's website with all of the content. So R for data science, we've talked a lot about this week. It gives a very good overview of the tidyverse. If you're interested in more statistics, so like regression, hypothesis testing, confidence intervals, I would highly recommend the Modern Dive book on the right. They do a lot more statistical things than we did this week. And then that middle book, Modern Data Science with R, is kind of a beginning to end data management. So it includes programming, some statistics, some machine learning, a lot of varied topics in that book. If you are interested in more R programming, there's a very good book by Hadley Wickham called Advanced R, which is all about how R works internally and how you can write better code. You can also write your own R packages. So we briefly wrote our own function when we were talking about bootstrap sampling, but we could also write an entire package. And they have a book here that describes how to do that. Again, all available for free online. And then finally, there's hands-on programming with R, which is an introduction to R as a programming language, but it uses data science, data analysis as kind of the context for talking about programming. So these are all really good resources for that. If you are interested in data visualization, there are some really good books talking about best practices for creating interesting graphics and informative graphics. So all three of these books, again, available for free online, do a great job of talking about how to customize ggplots and make graphics that are going to be meaningful to the people you're showing them to. If you want more machine learning, again, tidy modeling with R is a work in progress, but there's already a bunch of chapters that are up and available. Feature engineering and selection is going to be very much focused on the feature engineering that we spent a little bit of time on this week, but not a whole lot. So if you want more of that, this book is a great resource. And finally, hands-on machine learning with R is focused more on the machine learning methods and models. So they talk about random forest clustering algorithms, If you've heard of gradient boosting machines, neural networks, model stacking, basically anything, any type of machine learning model you want is going to be on in that book. And our final set of resources is R Markdown. If you want to learn more about reproducible writing, there's R Markdown, the definitive guide, which describes basically everything you could do with R Markdown. The R Markdown cookbook has popular how-tos for how to do different things in R Markdown. And finally, the Bookdown package is an extension of R Markdown, but that's really good for writing books. Like all three of these books were actually written in Bookdown. So you can write books, you can write articles if you're publishing research, or you can write like dissertations and stuff. So I wrote my dissertation using Bookdown as well. Beyond books, there are some blogs that you can follow to see interesting things people do with R. If you're interested, there's also the R Twitter community is very active. So I have a list of our community members that I keep pretty up to date if you're interested. And also there's a Tidy Tuesday challenge, I guess, that's organized by Thomas Mock, where every week he posts a new data set and people visualize it, tidy it, kind of see what they can find. And it's really just a fun, low-key way to play with different data and practice your data skills. All right. And so that is everything that I have. Thank you all for your participation and your effort this week. I know it was a lot of content. We do have a post-workshop survey that I would love if you all would take and provide feedback. That helps us make this workshop better in the future. So please do take that survey. All of our course materials are available on the course website. They will stay there till the end of time or until my web server decides that it will not host my website anymore. I will send out an email this evening once the final recordings get posted, but it will always be at this link. And then finally, do feel free if you ever have questions. This is all of my contact information. So please feel free to reach out in the future. And with that, I think we are done. We're about half an hour early, so not as early as I thought we might get out today, but hopefully everyone can get an early start on the weekend. Again, thank you all for your time and thank you for taking this course. Have a great weekend and a great rest of your summer.
Thanks, Jake.